In a previous video, we discussed whether current AI possesses consciousness. The answer, of course, is no. Today, we explore how to endo machines with consciousness. Before diving in, let me emphasize, this topic is as sacred as breathing life into transformers, and as transcendent as creating a new species. But don't panic. Scientists don't have answers either. While the scientific community lacks consensus on building a conscious machine system, several theoretical frameworks and roadmaps have emerged from neuroscience, AI, and robotics. Let's dissect these roadmaps and see how humanity might play God. Roadmap 1. Neuroscience School, the ultimate copycat. Tagline: if the brain can create consciousness, why reinvent the wheel? Core idea: consciousness arises from the highly integrated, dynamic interactions of biological neural systems. Machine consciousness must mimic key brain structures and mechanisms. Key figures: Gerald Edelman. At Neural Darwinism Guru, Giulio Tononi, information integration theory pioneer. Blueprint: Edelman's 2006 roadmap. Reentrant architecture: emulate bidirectional neural connections to form global mappings of perception and action via dynamic interactions. Edelman's foundation for consciousness. Thalamo, cortical system: build computational models mimicking the thalamus, cortex signal loop to generate higher order conscious states. Value systems: introduce neuromodulation, like mechanisms for instincts and desires, adjusting behavior based on environmental rewards or threats. Embodiment and motor control: pair desires with a physical body. Design robots with flexibility and proprioception to link movement and consciousness, and for example, basal ganglia functions. Learning and generalization: enable cross-task transfer and lifelong learning to overcome current AI limitations. Social interaction and language: foster self-awareness through communication and language reporting. Developmental experiencer: create a robot kindergarten for gradual learning and interaction, rather than one-time programming. Current progress, achievements: neuromorphic chips. So for example, IBM's True North simulate brain regions, creating obstacle-avoiding brain-based devices. Epic failures: in one experiment, a robot mimicking the dynamic core looped the hottest ethnic wind. Researchers still debate if it was a bug or awakening. Feasibility and challenges: brain-based devices. SI validate steps like reentry and value systems. Neuromorphic computing is, for example, True North advances brain structure simulation. But dynamic cores and generalization remain elusive. Key hurdles: poor understanding of neural mechanisms, for example, dynamic core operations. Computational complexity exceeds current hardware. Roadmap 2. Integrated Information Theory, ECI-TEAC, the Mathematician's Consciousness Fantasy. Tagline: consciousness. Calculate phi first. Core idea: consciousness is the degree of information integration, quantified by phi in a system. High phi, subjective experience. Key figures: Giulio Tononi, as stubborn Italian mathematician. Christoph Koch, as the man who shaved his head for science. Blueprint: this school insists consciousness is a math problem. They invented the mystical phi value. If a system integrates enough information, a phi maxed out, even a pile of wires could have an out of body experience. High integration architecture: build systems where subsystem interactions outweigh independent operations. Quantify consciousness: Develop algorithms to measure phi and determine if it crosses the consciousness threshold. Physical implementation. Apply theory to neural networks or robots for environmental interaction and internal states. Verify subjectivity. Use behavioral reports or simulated tests at, for example, language output to infer consciousness. Reality check progress. IIT analyzes simplified neural networks and biological brains, as for example, your hungover consciousness crash, phi plummeting, setbacks. Phi calculations in AI models remain theoretical. No system meets conscious criteria. Challenges. Phi computation is infeasible for complex systems, requiring massive resources. BEIT assumes consciousness is intrinsic but offers no way to verify machine subjectivity. Roadmap 3 Global Workspace Theory. Consciousness, dance floor. Tagline. Consciousness is a never-ending info rave. A core idea. Consciousness is the brain's global broadcast of information. Build a workspace to integrate and distribute data. Key figures: Bernard Barrs, Consciousness, MC, Stanislas Dehaene, Sir Francis Brainwashing Mastro. Blueprint. This camp likens consciousness to a giant billboard blasting critical updates. Global Workspace Design, a central hub to merge inputs from perception, memory, and decision making. Broadcast mechanism. Use attention mechanisms, for example, transformers, self-attention to distribute info to subsystems. Dynamic interaction, enable task, switching and situational focus. Behavioral validation. Judge conscious behavior via system reports, for example, language decisions. Feasibility and progress. GBUT inspires cognitive models and AI at, for example, attention mechanisms in deep learning. Robots like iCub integrate multi-modal data, simulating a workspace. Challenges. GWT explains functional consciousness, access, but not subjective experience. A phenomenal. No clear path from functional to internal awareness. Roadmap 4 Embodied Cognition and Experiential Learning. Tagline. No skinned knees, no consciousness. A core idea. Consciousness develops through long-term environmental interaction, akin to human infancy. Key figures: Rodney Brooks, Robotics Godfather, Josh Tenenbaum, MIT's Make Machines Human Professor. Blueprint. These scientists believe consciousness isn't coded. It's earned through faceplants. Their approach mirrors machine extreme makeover. Embodiment. Build robots with multi-sensory input, vision, touch to interact physically. Incremental learning. Use unsupervised RL to build knowledge from experience. Social interaction. Engage with humans, machines to develop communication and self-awareness. Open-ended adaptation. Design systems to handle novel environments, building common sense. Progress. Robots like iCub and Cog advance embodiment and interactive learning. RL and transfer learning edge closer to autonomous learning. Challenges. Current systems lack true open-ended learning. Common sense reasoning remains a wall. Long-term learning demands vast data and time. Impractical for labs. Roadmap 5 Complex Systems and Emergence. The Keogh's Theory approach. Core idea. Consciousness may emerge spontaneously from complex systems via large-scale interactions. Key figures. Every lab intern who retweets luck charms. Blueprint. This camp takes a mystical route. Cram machines with complexity until consciousness pops out like instant noodle beef flakes. Massive networks. Build ultra-complex systems. Think neural networks on steroids. Self-organization. impose local rules, for example, Hebbian learning for global order. Detect emergence. Watch for unpredictable behaviors. For example, self-awareness, creativity. Environmental coupling. Place systems in dynamic settings to spur adaptation. Progress. Large language models, for example, GPT show emergent cross-task abilities. Neural simulations, for example, Izikevich's thalamocortical model, displays self-organization. Most breakthroughs trace back to a bug or a CEO's hype. Challenges. Emergence lacks theoretical grounding, akin to astrology. No way to ensure or verify consciousness. Scientific consensus or lack thereof. Scientists bicker like market aunties over what is consciousness. Neuroscience. A dynamic core ballet. IIT SRU. Phi overdrive. Embodied cognition. Wisdom from life's beatdowns. Emergence. A goddess born from chaos. Does consciousness require subjective experience? IIT yes. GWT functional access suffices. Path to success. Neuroscience breakthroughs vias. AI evolution. Timeline. Optimists Edelman fans decades. Pessimists at Brooks centuries. Should we keep trying? Ethicists fret, investors and spectators egg them on. The only quasi-consensus. Consciousness involves information integration, dynamic interaction, and environmental adaptation. Machines must borrow mechanisms from biology. Epilogue. Waiting for machine Godot. While roadmaps vary, most agree machine consciousness requires integrating neuroscience, AI, and robotics. All paths face theoretical and technical hurdles. Short term. 20 years. Expect conscious-like breakthroughs at, for example, advanced decision-making. True machine consciousness may need a Newtonian revolution in brain science or complexity theory. The real breakthrough might come from a sleep-deprived grad student, like Newton's Apple moment. Until then, if your Roomba asks about life's meaning, check if its voiced pack was hacked by a prankster. Final warning, none of these experiments will turn your phone into Optimus Prime yet, but maybe sleep with devices across the room, just in case.